We discussed in our previous lectures how to model uncertainty using probabilities and how to integrate them in our learning decisions. We discussed now how we can estimate these probabilities from a given training set. We assume that the training data is drawn randomly from a known distribution such as a Gaussian distribution. We can then estimate the parameters of the distribution from the training set and use it to make a decision based on the maximum likelihood estimation method. We also introduced the bias variance dilemma and some model selection methods for trading off model complexity and empirical error. Throughout this unit, we assume that we have unidimensional samples, and we will discuss the case of multidimensional samples in the next unit. Let's say that we have an independent and identically distributed sample X made of a number of sample points xt, where each one of these xt was drawn from some probability distribution with some unknown parameters theta. And the whole problem of parametric estimation is that of estimating theta using the sample we have in front of us. In other words, in terms of machine learning, in terms of the training set we have. And so to do this, we are assuming some model for this distribution. For example, we will assume that our sample is coming from a Bernoulli distribution or from some multinomial distribution, or maybe sometimes from a normal distribution. And the main question we are going to look at is which values of theta in that model that we are assuming make sample X most likely, and I'm going to formalize in a moment what likely means in this context. The main thing we are going to look at is the maximum likelihood estimation. And the way this goes is like this. You are going to think about the likelihood of some parameter theta given the sample X. In other words, what's the most likely value of parameter theta which explains the sample X we have in front of us. And so we have this notion of the likelihood of theta given X, which is written here on this slide, and that's going to be the probability of seeing sample X given theta. And because we have a number of points which are independently and identically distributed, this translates into this joint probability, which is of the form a product of the probability of seeing each one of these points given parameter theta. And so one very common trick we have when we have such a big product is that we apply a logarithm so that the product becomes a sum. And so we discuss about the so-called log likelihood, which is nothing else. So this is denoted by capital L of theta given X. Is nothing else than the logarithm applied to this likelihood of theta given the sample X. So when you apply logarithm to this one, then of course you have, instead of a product, you have sum, and then the logarithm goes inside the sum. So it's a sum for all the points in your sample of the logarithm of the probability of seeing that point given parameter theta. And so the question is going to be, can we find that value of theta which maximizes this log likelihood? So this is the maximum likelihood estimator for parameters theta. And I'm going to take a few examples to see how this looks like in the case of a few very common distributions. So here is our first example, that of a Bernoulli distribution. And just to remind you, this is about the case where you have only two states, 0 or 1, or maybe failure, success. And so your X is going to be a binary variable with values in 0 and 1. And the probability of X is going to be given by this sort of formula, P0 to power X times 1 minus P0 to power 1 minus X. And this is nothing else but saying that the probability of seeing 1 is P0, and the probability of seeing 0 is 1 minus P0. And so in this case, we will have the log likelihood to be capital L of P. So this is our parameter theta from the general case. In our case is this probability p0. So I'm writing here in the form of p. So the log likelihood of p given sample x is simply, as we discussed before, the logarithm of this joint probability distribution. So that's a sum. We have n points in our sample, and in each case is the probability p to power xt times 1 minus p to the power 1 minus xt. And I hope that this is not going to be confusing. It's not x2 power t, but it's x index t, but we put this index into the exponent as we did before, because as you will see in just a moment, we may have some indices here, some several components for x. So again, I hope this is not confusing. This is not to say x to power t, but it's really x index t. So, and x index t is a variable taking values 0 or 1. And so this is now, it can be developed further. Logarithm goes inside and the product becomes a sum. So this is sum from 1 to n by x to power, so xt logarithm of p plus n minus the sum from 1 to n of xt times logarithm of 1 minus p. And we want to find out, so calculate that value of p that maximizes the log likelihood. And to do that, we are simply going to take the partial derivative. So it's going to be dl p given x by dp applied to p hat. This has to be equal to 0. So when we do that, this is a very simple calculation. The result is going to be that p hat, so the estimator, has to be exactly 1 over n sum from 1 to n of xt. And I hope that this makes sense intuitively, because as we discussed, x is a Bernoulli variable with probability of success p. So the expected value of x is p, and the maximum likelihood estimator of the mean is the sample average. Now, one thing that is more subtle is that you have to realize that the estimate is a function of the sample, and in fact it's a random variable itself. So we can talk about the distribution of this estimate given different samples. We can discuss how the variance of the estimator goes down as we have larger n, that is to say, as we have samples of higher size. Here is another example, that of a multinomial distribution. So remember, this was a generalization of Bernoulli. So in this case, we have not just two states as in Bernoulli, but in fact we have k states with k larger than 2. And the result of this distribution is going to be a number from 1 to k. But you can also think about it, and we have done this before in one of our previous lectures. You can also think about it, we called this a one-hot encoding. You can think about it as having in fact k binary variables. So each one of these takes value 0 and 1. And as a matter of fact, only one of them has value 1 and the other ones have value 0. And the idea is that that variable which has value 1 indicates the state that was selected by the current sampling. And in multinomial distribution, the probability of getting such a distribution was the product of pi to power xi, where pi is the probability associated to state I. So let's say that we do n such independent experiments, and we have as an outcome the sample x, which is made of these data points x1 all the way to xn. And as a matter of fact, just following this encoding, each one of these points can be seen as a vector, and is going to be a vector of exactly k components. And in fact, as we just mentioned, each one of these components is going to be 0 and 1, and it's 1 if experiment T chooses state I. And it's going to be 0 otherwise. So this in effect makes this vector a one-hot encoding. Only one of the components is 1 and all the other ones are 0. So in addition, that's another way of saying that the sum from 1 to k by xit, this has to be exactly equal to 1. And this is true for all of these t's from 1 to n. And so the maximum, in this case, the maximum likelihood estimator for our parameters, which in our case are these probabilities of each one of the states. So this is, in fact, I'm just going to write and then I comment. It's exactly this. Pi hat is 1 over n sum from t with t from 1 to n by xti. And we can derive this in two different ways. One is you can think about the multinomial as being k separate Bernoulli experiments, and then you are applying the equation that we just, or the solution to the problem, to the Bernoulli problem that we just derived on the previous slide. And the other method of solving this is by writing the log likelihood in this case. So we would apply the log to the likelihood estimator, and we would take the partial derivatives with respect to each pi, we would put them to be equal to 0, and then we would derive, just like we did for Bernoulli, that the solution is going to be exactly this one that we wrote at the end of this slide. Here is just one more example, in case we have our samples distributed normally with some mean mu and variance sigma squared. And so in this case, the probability of seeing a sample x, and remember in this case x can be anything from -infinity to +infinity, but because it's distributed normally, the probability of seeing mu is exactly 1 over square root of 2 pi sigma times exponential with parameter minus x minus mu squared over 2 sigma squared. And so the x is going to be between -infinity and +infinity. And now, if we had a number of experiments, and we have in front of us a training set or a sample x, which consists of a number of such points. So this is going to be again xt, and again I hope this is not confusing. This is not to say x2 power t, but it's really a number of samples. So xt with t from 1 to n. and each one of these xt's was independent and distributed exactly according to the same distribution, so normal with mu and sigma squared. Then the log likelihood, so the log likelihood, in our case the parameters are mu and sigma, so the log likelihood of having mu and sigma given this sample x we have in front of us is simply going to be again by applying the logarithm to the likelihood estimator. We get that in this case it's exactly minus n over 2 logarithm of 2p minus n log sigma minus sum with t from 1 to n of xt minus mu squared over 2 sigma squared. And so to solve the problem of the maximum likelihood estimator, by the way, I'm going to abbreviate this just so that I'm saving some space by MLE, so maximum likelihood estimator. So to calculate this, just like before, we are going to take the partial derivative of this log likelihood with respect to mu and with respect to sigma, and we get two equations with two unknowns, and we solve that system of equations, and we get that the solution is m is going to be 1 over n sum from 1 to n of xt, and we get that s squared, so this is the estimate for sigma squared, is exactly 1 over n sum from 1 to n by xt minus m squared.